Hello there, welcome to section 1 of Unit 2. In this unit, we'll be looking at energy, fluid dynamics, viscosity, and elasticity. And in the first session, we'll be talking about work and energy. Let's look at the objective of section 1. The first objective is for us to be able to explain the term work, define energy, state the relationship between work and energy, list the forms of energy, explain the concept of energy conservation, and also solve some problems related to work and energy. I'm sure we all have an entirely different meaning of work, and most of the times we explain it considering labor. But work is said to be done under these two conditions. And the first one is a force must be applied, and two, the applied force must produce a displacement in the direction of the force. So we explain work as a work is said to be done by a force when the force produces a displacement in the body which it acts on in the direction of the force. And mathematically, we express work done to be equal to a force times the distance moved in the direction of force. And the unit of work done is joules. That's Newton times meter. Let's look at work done by a constant force. That's force acting on an object at an angle theta to the direction of the displacement. So like what we have here, we have a box on the ground and we have a force acting on it in the direction of s. But this time around, the force can also act at a particular angle. So anytime we want to calculate the work done, meaning we have to put the angle into consideration. But should in case it doesn't form any angle and it moves just straight like this, meaning we are going to get the angle to be 0, which we are still going to get force times displacement because the sine theta is going to be 0, or that the sine 0 is going to be 1. Then we're just going to get Fs. That's the force times the displacement. But should in case the force acts at a particular angle, say theta, then we have to put the angle into consideration. So that our work done right now becomes F cos of theta times the displacement of S, or the force times the displacement times cos theta. Let's look at some special cases here. The case where we can have a work done to be 0, a work done to be positive or a negative. So should in case we have your theta, that's the angle in which the force is being put through, then we say that to be 0, the theta is 0, then we say that the work done is is positive. But in the other way, should in case our theta is 180 degrees, it means that after finding the cos of 180, we are going to get negative, and meaning our net work done will be negative. Let's look at the one that we also have theta to be 90, and we know that cos 90 is is 0, meaning our work done will be will be 0, meaning a work done through a force that is perpendicular to the distance is is 0. Now let's consider a particle being displaced along the x-axis under an action of varying or changing force. The particle is displaced in the direction of increasing x, that's the displacement, from xi, that's our initial displacement, to xf, that's our final displacement, as displayed in the diagram below. But should in case we have, or we assume that we have fx versus x curve is divided into a large number of intervals, said that our total work for the displacement from xi to xf is approximately the sum of such terms, then we are going to have our work done to be equal to the summation of fx changing x. Kinetic energy. Here we are going to prove how we had the kinetic energy formula to be 1/2 mv squared. We know from our kinematics that v squared is equal to u squared plus 2as, where v is our as our final velocity and u is our initial velocity, a is our acceleration, and s is our displacement. We can make s stand alone by doing a little substitution here, where we are going to get v squared minus u squared all over 2a. We also know that a work done is equal to force times a displacement, where we have the theta to be equal to 0. We can represent f, that's ma, to be ma, that's ma, and substitute it in the work done formula, so that we will have W to be equals to what? ME, that is the force times the displacement. And we can replace as displacement formula that we done earlier here, so that we get MA to be equals to what? The displacement, that's the V squared minus U squared all over 2A. We have A here, we have A here, that's the acceleration, which can cancel out, and we get this one. So should in case the body has an initial rest to be equal to 0, meaning our U is going to be 0, and we have our final answer to be what? MV squared over 2. The work done is equal to kinetic energy of a body, so that we will get our kinetic energy to be equal to what? MV squared over 2, which is the same as 1 over 2 MV squared. Let's look at the conservation of forces. So there are two important properties that we have to consider here. And the first one is a force is conservative if the work done on a particle between any point is independent on the path taken by the particle. And the second one is the work done by a conservative force of a particle moving through at any closed path is what? Is 0. So in general, the work done on an object by a conservative force is equal to the initial value of the potential energy associated with the object minus the find value. So we say that a force is conservative if it causes a change in mechanical energy E. And what we are talking about, that is the mechanical energy, is the sum of potential energy plus the kinetic energy. Let's move on to potential energy. What is a potential energy? Potential energy is the energy that is possessed by virtue of its position in a force field. And where we have our potential energy to be equals to what? mgh, where we have the m to be the mass, the g as the acceleration due to gravity, and h here is what? Is the height. So in case we have a fruit like a mango hanging on a tree, it's also having a potential energy because of virtue of what? Its position. For the proof of a potential energy, we know that work done is equal to what? Force times what? A displacement. But this time around, a displacement is our height. And we also know that force is already equal to what? MA. And the MA can be represented by G. That's the acceleration due to gravity this time around. Because when a mango is hanging on a tree, it has its own acceleration, which is pulling it to the ground. That's the acceleration due to gravity. So we can substitute the F equals mg into W equals what? Fh, so that at the end we get our potential energy to be equals what? mgh. Let's look at power. What is power? Power is the work done per unit time, and the rate of doing a work we say what is power. So mathematically we represent power as what? The work done over the change in time. And the average power can be defined as the average rate of work, that's our W, or work done, that's our W, and it is obtained by dividing the work done by the time required to perform a work, and it's also what? Work done over time. The unit of power is joules over second because it's work done over time, or you can represent it by what? Big W, that's watts.